Okay, so today we're going to talk about quantity stoichiometry. Basically, what we're going to be looking at is how to turn predictions related to our number of moles that we have into a certain quantity. So in other words, an amount of grams, for instance, or perhaps even an amount of liters. There's going to be quite a bit of different things we're going to cover today. Let's get rolling. So we're going to start with a quick review of basic stoichiometry from last class. In other words, just predicting moles like we did yesterday. Then we're going to introduce quantity stoichiometry. Like I mentioned, this is basically finding amounts of products or reactants given a quantity, often not given in moles. So in other words, if I'll say how many grams of this was produced, that's what you'll be looking for here. Now, about halfway through the lesson today, we're going to need to review some gas law content. So that was the stuff from our second unit. Um, it has been quite a while since we've talked about a lot of that stuff, including the ideal gas law. So we will go over it. I'll actually get you to like maybe write a few things in your notebooklet on top of what's already in there, just to provide you a little bit of extra background. So it's a little easier for you going forward. Anyway, let's move on. So topic 2, quantity stoichiometry. This is page 8 in your booklet that you received. Mole to quantity. If you're given moles of one substance and are asked to find the mass, concentration, or volume of another substance, this is a mole to quantity problem. So in other words, unlike before where we were just looking at moles to moles, we're now looking at how to turn moles into a certain quantity. Because moles are given, it is possible to directly convert using mole ratio and finish by converting the new moles to the desired quantity. Basically, in plain English there, what this means is if you have your chemical equation, so something becomes something, the only thing that's going to connect all the different pieces inside of this are your molar ratios, right? So if there's like a 2 here and a 3 here, the only thing that's affected by that is moles. Everything else is not affected by that. So you'll need to come back to moles and then figure out the relations and then go back to whatever quantity, like grams or liters or whatever, that you're looking for. So we'll start with an example. And again, I didn't mention before, but we actually have done this kind of stuff before. So this is still review, which is nice because that's starting our online learning a little bit easier than it could have been. So for this first example, copper metal reacts with an aqueous solution of silver nitrate to produce silver metal and copper 2 nitrate. What mass of silver can be produced by reacting 0.250 moles of copper? Just like before, you need to start with a balanced equation. So again, we're reacting copper metal with aqueous silver nitrate. I'm not going to worry about the state so much here. You can put it in if you want. I just think it's a waste of time, at least in this situation. So copper, Cu, plus silver nitrate. Well, silver has a positive 1 charge, and nitrate, which is NO3, that actually has a negative 1 charge. That looks like an H that I did there. Hold on, I'm gonna fix that. That is a 1 positive. There we go. 1 positive for the silver. NO3 is a 1 negative. In other words, this is just going to be Ag, that's silver, and NO3, right? So that way it's an ionic compound that is balanced. When you combine these two together, this is going to form silver metal, so just Ag on its own, plus copper 2 nitrate. So we're saying copper has a 2 positive charge, nitrate has a 1 negative charge, so you swap and drop. It's going to be CuNO3 in its own set of brackets here with the 2 in the outside because we need 2 of these to balance out the charge of the single copper. Next up, of course, it is a balanced equation, so we have to make sure we have the same on both sides. Notice we have 2 nitrates over here, but only 1 nitrate right here, so we should start by putting a 2 in front of this. And then to balance it out, we'd have to put a 2 in front of the single silver right there as well. Step 2, list your unknowns and givens. Well, one thing that's given is we know how much copper we have. It's 0.250 moles. The thing that we want, though, so our unknown, the thing we want, is the mass of the silver. So the mass of that Ag. Well, just like before, we need to figure out how many moles of Ag we have before we can figure out the mass of our Ag. Ag, of course, being silver. So looking at your mole ratio, notice we have 1 part of copper, and then we have 2 parts of silver. So that means since this copper is only representing 1 part, we have to times that, there we go, we have to times that by 2 to turn it into 2 parts for silver. So for silver, if you just take 0.250 and multiply it by 2, you have 0.500 moles. So that is how many moles of silver we have. And then to turn moles into a mass in grams, we have to use the molar mass. So this is where you'll actually have to look at your periodic table and figure out what the molar mass of silver is. The molar mass of silver, according to my periodic table, is 107.87 grams per mole. And I always just use the units as its own little formula, right? If I know my units are grams per mole, then that means my formula has to be some amount of grams. So I'll say X grams over some amount of moles, which we know is 0.500. To solve for X, we just need to multiply that 0.500 over, and this is going to give us X equals, I guess to only, what is it? I guess it's only 3 sig digs in this question. That'll be 53.9 grams. And again, I just multiplied this 0.50 over to the other side. All right, we're going to move on to the next question here. Sulfuric acid is neutralized by sodium hydroxide solution. What mass of sodium sulfate can be produced by reacting 0.350 moles of NaOH? That's your sodium hydroxide. First of all, let's kind of break apart what this question is saying. It's saying the sulfuric acid is being neutralized. So a neutralization reaction always produces 2 things. The first and foremost thing it produces is water, H2O, although we'll usually write it as HOH in a neutralization reaction, and I can show you why in just a second. And the other thing it produces is something that's called a salt, which is a bit of an umbrella term. It always forms when you mix an acid with a base. We'll worry about that when we write it out. Let's first start with our formula for sulfuric acid. Sulfuric acid is hydrogen sulfate, which is H2SO4. Now, full disclosure here, if you didn't know what sulfuric acid was, in your data booklet, there's that acid and base chart. Sulfuric acid can be found on that. So you can just look up the formula right there. Anyway, plus we have sodium hydroxide, so NaOH. And this is going to form 2 things. The hydrogen and the hydroxide are going to combine to form HOH, which is just water. You could have written it as H2O. I don't though, because I prefer to see where this OH goes. Notice the OH is on the NaOH and then it's also here. Just becomes a little easier that way in my opinion, but it's up to you. Plus the leftover, the salt, quote unquote, which just needs to be the other compound that forms from a double replacement reaction here. So your sodium, your Na, is going to have to tackle on to the sulfate. Now, just kind of an FYI here, sodium on its own has a +1 charge. I'm not really sure where to write that, but it has a +1 charge. Sulfate, which is SO4, has a 2 negative charge. So if you swap and drop this, that means you're going to need 2 sodiums, so Na2, and just a single SO4. Okay. Next thing, of course, this does need to be a balanced chemical formula. One thing I noticed right off the bat is I have 2 sodiums here, but only 1 sodium here. So I need to put a 2 in front of my sodium hydroxide. And then that means we have 2 hydroxides now. So I'd have to put a 2 in front of the HOH. So we have 2 hydroxides. And that was actually quite nice because now we have 2 hydrogen on both sides as well. So this is now fully balanced. The next thing I guess I should do is identify what I've got. So I've got my 0.350 moles of NaOH. So I'm going to say that amount right there is 0.350 moles. And I want you to notice that that's equal to 2 parts because of this 2 coefficient right out in front. What we're interested in is how much sodium sulfate can be produced. Sodium sulfate is this guy right here. So we want to know how much in terms of a mass of this sodium sulfate is going to be produced. Well, before we can predict mass, we have to use our number of moles in this balanced chemical formula. We know that this 0.350 moles represents 2 parts, and we can also see that we only have 1 part of sodium sulfate, and you can put a 1 in front of that if you want, 1 part of sodium sulfate. So we just have to take this 0.350 and divide it by 2. And that's going to give us 0.175 moles of sodium sulfate. Now you might be asking, how can we turn moles now into a mass? Well, hopefully what you just said under your breath at your own screen right now, or maybe you didn't, is use your molar mass, right? So in other words, you got to look at your periodic table to figure out what your molar mass is going to be here. Notice we have 2 sodiums, so we're going to have to use 2 times the molar mass of sodium, which is 22.99, plus a single sulfur. Well, a single sulfur is 32.07, plus 4 oxygens, which is 4 times 16.00. So in total, this molar mass is going to equal 142.05 grams per mole. And then, of course, like I mentioned before, you just need to set how many grams you have, which is what we're looking for. So X over how many moles you have, which is 0.175, and just multiply that over. And we are going to get X equals to, I guess, just 3 sig digs as the question kind of listed out, 24.9 grams. Whew, there it is. There's a lot to this one. There's a lot of bouncing around. The main idea, though, is make sure you start with your balanced chemical equation and then only focus on how many moles you have, right? So if I give you how many moles, that's what you can use to kind of unlock any other parts of your chemical equation. All right, example 3. I actually would like if you guys, well, I was going to say I'll get you guys to pause and try this on your own. You can pause and try it on your own if you wish, so feel free to do so. But if you didn't feel like doing so, or if you're now unpaused right now, I'll show you how to go about this question. So when you have sulfuric acid reacting with sodium hydroxide, sodium sulfate and water are produced. This time it gives us a quantity of H2SO4, that's your sulfuric acid. And it's reacting with a certain number of moles of your sodium hydroxide, your NaOH. But we're looking for a concentration of the acid. Remember concentration from before. This was just a unit we just kind of cleared up not that long ago. Concentration is measured in moles per liter. It could be measured in other things as well, but when we ask for the concentration, we're pretty much always talking about moles per liter. So I think a good thing to start with would be to actually write out your balanced chemical formula. We got sulfuric acid, H2SO4, reacting with sodium hydroxide, NaOH. This is the same formula from before. It's producing water, HOH, and sodium sulfate, which was Na2SO4. And just remember, we had to put a 2 in front of this and a 2 in front of this. And bingo, bango, bongo, that thing is now balanced, right? No big deal. Now, we do know how many moles of NaOH we have in this case. We have 0.150 moles. Once again, this represents 2 parts. We're looking for the concentration of the acid. The acid in this case is this guy, the H2SO4. Once again, though, we know we have 2 parts of NaOH, so we just need to divide this by 2 to figure out how many parts, well, 1 part rather, how many moles, I should say, of our acid we have. If you go 0.150 and divide it by 2, you're going to end up getting 0.075 moles. Now here's the fun part. This is how many moles of sulfuric acid we have. We're not looking for the number of moles as our final answer, though. We're looking for the concentration of the acid. Concentration is measured in moles per liter. So in order to find this, we would need how many moles we have, which we've got, and we would need to know how many liters we have as well, which we also have. Well, we have milliliters, but same idea, right? So to find our concentration, I'm going to say C equals, concentration equals, how many moles we have, 0.075 moles, divided by how many liters we have. Just take this and divide it by 1,000. So it's going to be 0.040 liters. This is going to give us a concentration to just 3 sig digs of being 1.88 moles per liter. So again, the moral of the story on these ones is be a little bit creative with what you're looking for. In other words, try to figure out what you've got and how you can get to what you want. If we're looking for a concentration, that means we need moles and liters to find the moles per liter. The good news is moles is what connects this whole thing all together. If you don't have moles, you are out of luck. All right, so here's where we have like a little bit of review. I'm not 100% certain where you can write this, to be honest, but like on your page 9 right now, it says like quantity of, or 2 moles, like there's a typo there. If you could write that kind of like either just above that or even in that little tiny gap between that paragraph and example 4, it would probably really help you. As a matter of fact, I'm going to tell you, you don't need all of this information. If there's only some things that I get you to jot down, I'd like you to jot down the combined gas law. So you'll want to put this formula on there. This says the initial pressure times the initial volume divided by the initial temperature equals the final pressure times the final volume divided by the final temperature. This was really nice for when you're comparing a before and after situation. So in other words, when you have a gas that is either going under an increase or a decrease in either pressure, volume, or temperature, the combined gas law works wonders. It really makes it a lot easier. The other thing that you need to jot down is the ideal gas law, which we're actually going to use a lot today. That's PV equals nRT. So in other words, your pressure times your volume equals your number of moles times R, and R is always 8.31, so maybe you want to jot that down too, times by your temperature. Another thing I just want to remind you, temperature is always in Kelvin. It is never in degrees Celsius. And remember, to get Kelvin, you just take your Celsius and you add 273.15 to it. Okay, so you might want to jot that in there, right there as well. One last thing that I need you to jot into your notes, and again, I apologize that there's so much to copy in, is the definition of STP and SATP. So remember, STP stood for standard temperature and pressure. This is, by definition, 273.15. Oh, hold on, this is backwards. My mistake, guys. I need to actually switch these around. Holy smokes! See, look, I've made a mistake. I was even like thinking, wait a minute, something's not right here. STP is 273.15 Kelvin. That's 0 degrees Celsius. However, it is 101.325 kilopascals. SATP, standard ambient temperature and pressure, is 298.15 Kelvin. That's 25 degrees Celsius. And that is 100 kilopascals for the pressure. I apologize. I should have switched those around. That is certainly backwards. Just make sure you've got that in proper order. Again, I apologize. I don't know how that happened. I must have slipped up. But I do know it's this other order, so we're good. Anyway, we're going to need this for the next couple questions here. Let's get rolling. So first of all, quantity to moles. When the quantity of one substance, such as mass, volume, or concentration, is given, and you're asked to find the moles of another, you have to provide or perform a quantity to moles calculation. So in other words, this is the same idea as before, just working backwards. The only trouble is oftentimes these questions throw ideal gas law or combined gas law kind of questions at you. So first of all, how many moles of water vapor can be produced by reacting 78.4 liters of oxygen gas at STP with a sufficient amount of hydrogen gas? Well, as always, start with a balanced equation. We're combining oxygen and hydrogen. So in other words, we can say H2, that's hydrogen gas, plus O2, that's oxygen gas, is going to produce H2O. And to balance this, we'd have to put a 2 in front of this because we need 2 oxygens on both sides. And now we have 4 hydrogens, so I'll have to put a 2 in front of this here as well. Step 2, list your unknowns and your given. Well, we know for our O2, our oxygen, we know we have 78.4 liters. We also know that we're dealing with STP conditions. So that means we also know our pressure is 101.325 kilopascals. And we know our volume, oh, sorry, not our volume, what am I talking about? Our temperature is going to be 0 degrees Celsius. So in other words, we'll say 273.15 Kelvin. I guess the thing that we want in this case is we want the number of moles of water. So moles of H2O. So in order to find the moles of H2O, we're going to have to take this quantity of oxygen that we were given, and we're going to have to turn that into moles somehow. Well, I want you to notice we have a volume, we have a pressure, and we have a temperature. From before, the ideal gas law says PV equals nRT. We already have a pressure, we already have a volume, we're looking for a number of moles. R is always 8.31, and we have a temperature. So we have everything we need here in order to solve for N, right? So we can throw these numbers in here. So we'll say 101.325 times your volume, which is 78.4, equals N times R, which is 8.31, times your temperature, which is 273.15. We just need to divide away the 8.31 and then divide away the 273.15. This is going to give us our number of moles as being 3.499697. And that is our number of moles of oxygen. One last thing to do here, guys. So we found the number of moles of oxygen. Notice that's 1 part. Look at how many parts of H2O we have. We have 2 parts of this. So in other words, if we're looking for the number of moles of H2O, we now have to times this by 2. So our number of moles for water is going to be rounded to 3 sig digs here. It's actually going to be a nice 7.00 moles if we rounded it to 3 sig digs. Okay, so it looks like we got a couple more questions here. Let's actually take a look at these before I do them real quick. You know what I'm going to say? I want you guys to try question number 5. So I do want you to pause the video here and give this one a try on your own. And then I'll go over it in just 1 second. Okay, I'm going to go over this one now. Hopefully you were able to get it right, but let's have a look. Always start with your formula. So in this case, since we're reacting zinc with hydrochloric acid, we're going to say it's zinc, Zn, plus HCl is going to become, this is just going to be a single replacement reaction. So zinc is going to combine with the chlorine. Zinc has a positive 2 charge, so it has to be ZnCl2 and H2 gas. Remember, hydrogen does not exist on its own. It has to form H2. To balance this, we only have to put a 2 in front of the HCl, and then that thing is all balanced. One thing we know is we know how much zinc chloride we have. We have 450 grams of that. But 450 grams is useless for actually going from one thing to another in a equation. We actually have to turn this into a number of moles. And to turn a mass into a number of moles, we need the molar mass. So if you look at the molar mass of zinc chloride, zinc is 65.41, and we have 2 chlorines, so 2 times the molar mass of chlorine, which is 35.45. This is going to equal 136.31 grams per mole. Now we just set that up as a little equation on its own. 136.31 grams per mole is going to equal some amount of grams, which we know, 450 grams, over some amount of moles, which is what we're looking for here. Multiply by n, divide by 136.31, and you're going to find that n is equal to 3.301299 moles. That's how many moles of zinc chloride we have. We're looking for how many moles of zinc we would need. And notice that since we have 1 part of zinc chloride and 1 part of zinc, these numbers are actually going to be the exact same thing, right? So we just want to round now to, I guess, 5 sig digs. That's kind of crazy, but whatever. So rounding to 5 sig digs, we'll say the number of moles we have is actually 3.3013 moles. Okay, here's another one. Last example. This has been a very long lesson. I apologize, guys, but hey, it's better than like the full 80 minutes or 90 minutes or whatever we usually get. So example 6. You know what? Just taking a look at this one. You can do this one on your own as well. Pause the video here. Give this one a try. All right. So we got a lot of weird stuff going on here. We know we have a certain volume, right? So we see milliliters right here. And we also have this right here, 3.00 capital M. Remember, capital M is just moles per liter. Now, since we know the volume and we know moles per liter, you can just multiply these two things together to get how many moles of H2SO4 you have. We'll come back to that a little later, but just good to know. So we know we're mixing sodium chloride with H2SO4. That's sulfuric acid from before. So that's going to produce hydrochloric acid and sodium sulfate. So if we write out the formula for this, as we always should do first, sodium chloride is NaCl plus H2SO4. This is going to produce HCl, hydrochloric acid, plus sodium sulfate, which we've seen before as well. Remember, sodium has a positive 1 charge, sulfate has a 2 negative charge, so you swap and drop, it's Na2SO4. And then to balance this, we need to put a 2 in front of the sodium chloride to make sure we have 2 sodiums on both sides. Now we have 2 chlorines here, so we need to put a 2 in front of this guy as well. And I think that's now balanced. From here, we know how much H2SO4 we have. We know its concentration is 3.0 moles per liter. And this is going to be equal to some amount of moles over some amount of liters, which we actually know, 0.0269 liters. Multiply that over to the other side, and you're going to see that N is going to equal 0.0807 moles. And realize that that right there is just 1 part, because there's only a 1 in front of this. We're looking for how many moles of sodium sulfate are produced. Notice sodium sulfate is only 1 part as well. So what do you know? It's the exact same amount. We can say it's N equals 0.0807 moles. And I think now that I'm looking back at this, as I'm like looking at my answer key, I was wondering, why did I round this so soon? It's probably because I saw the writing on the wall. I probably knew, hey, there's the same different number of moles for these ones. We won't have to worry about it. Whew, all right, anyway, that was quite a rambling lesson. I apologize for that, and I'm sorry for that mistake in the center. Take my word for it, though, that was correct. So be sure to complete the questions on page 6 and 7 from last class if you haven't done that already. And then I want you working on page 11 to 14. Now, here's a little bit of a heads up. There's lots of questions in here. And if I'm going to be real with you, I'm going to say it's actually too many questions. If I were you, like, and you got my permission to do this, on page 11 to 14, just focus on every third question. So in other words, only do the question numbers that are divisible by 3. So do 3, 6, 9, 12, 15, blah, 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 right? I think there's like 20 questions in there or something. It's way too much. You don't need to get that much practice at this, but focus on every third question. And if you're still finding yourself kind of stumbling, that's when you should go back and try some more. I want you to remember, though, the answers are in the back of the booklet. And if you need any help, contact me over Zoom. Like dead serious, please do that. That's what I'm there for. And aside from that, best of luck.